Welcome to surveying class. So today we'll be discussing lecture number 10, electronics measurement of distance. So we are into unit 3, that is last lecture in unit 3, measurement of horizontal distance. So in this unit basically we are discussing how to measure the horizontal distance on a site. So in the first lecture of unit 3 we have discussed using tape or using chain basically how we can do in different conditions. Also we have seen the ranging, right? Direct ranging, indirect ranging, all these things we have discussed. Then in the second lecture in unit 3 we have discussed the errors associated with the horizontal distance. So while taking the measurements and all, definitely we will encounter the errors on a reading. So that in details we have discussed how to encounter what are the different sorts of errors in the linear horizontal distance measurement and how to overcome this, all these things. So this is lecture number 10, that is third lecture in this unit 3. Here we'll be discussing about electronic measurement of distance. So now the next question comes, why we need electronics measurement system. So in the earlier two lectures you have seen the main objective, right, in this unit or basically in the surveying is basically to, when you have an entire area, to find it, to locate the objects, right? For example, this is a control point, so from the control point you are measuring what is this horizontal distance, right? So this distance can be measured using chain or tape on a field, but as we have seen, the field or the terrain is not maybe smooth as showing in the picture. There may be many obstacles in the middle, right? And that terrain also may not be a flat terrain. There may be undulations in the terrain, or there may be many difficult terrain you may encounter. There may be a tree on this middle. In that case you have to use some indirect ranging. We have seen different difficulties also whatever we are facing on a site. So to overcome this type of uncertainties, we use electronic electronic instrument for measuring the horizontal distance. So this on and using those electronic instruments, the accuracy of our measurement will be good, and we will get the better results. So the direct measurement of distance using the tape is difficult when the terrain is rough or site is congested. Like if you have many trees and all, it is very difficult, right, to first set the straight line, that is we call it ranging, and then you take the measurement. So it will be difficult. Even the indirect measurement of distance using the optical method is not suitable for high accuracy. So you have seen in the last lecture also, the accuracy is a very major concern in the horizontal distance measurement. Using the tape also we won't get our required accuracy. Similarly, even if using the optical methods like by sending the lights, that also the accuracy is not good. So thus to obtain high accuracy measurements in difficult terrain or for the long distance, right, if the distance is also very long, in that case what will happen, we have seen in the earlier lectures, right, if a and b, a point is here and you have the b point is here, a is b is very far, maybe for example 5 kilometers for example. So in that case what will happen, so what we have to do, we have to take intermediate points, right? So here one point, so here one point, like that intermediate points we have to take, and each point you have to measure the distance. So what is the distance measurement of this one, this one, this one, like that, all intermediate distances you have to find out, and if we sum it you will get the total distance, right? So now what is the problem with this? Means there will be errors in each measuring, right? It will be accommodated in the total count also. So that is again the problem, because our tape is limited, right? Tape length is limited. It may be 20-meter, 30-meter, 40-meter, 100-meter tape is maximum maybe available. So beyond that you cannot measure. I mean, we have to take the intermediate points for the long distance measurement. Thus the electronic instrument is such, in that case, is very useful, where in a very long distance also you can measure is electronically. So that is the use of electronic device, electronic instrument for measuring the distances. So what electronic instrument we are using? So electronic measurement of distance is carrying out by either by using electro optical device coupled with reflector, also called laser range pole, or a pair of electromagnetic instruments. So what we will do, there will be an instrument, that is this instrument, we call it EDM, right? Electromagnetic distance measurement, EDM. And this type of small instrument will be mounted on a tripod, and then at the far, where up to which distance you want to measure, right, in that point you place a reflector. So this type of small reflector, basically it is a mirror type reflector or prism type reflector will be there, where small prism will be there inside. So from the EDM, basically we are sending the signals, either it may be optical signal or it may be electromagnetic signal also, depending on the instrument. It will be sending the signals, and this signal will be reflected into the mirror, and again it will be received in the EDM. So EDM will count, right, how much time it takes the wave to travel from this point to this point and again reflected back to this point. So it will measure the how much distance, how much time difference between the emission and the reflection, and based on that it will count what is the distance. So that is the principle, and this is the instrument basically we are using, DM, right, electronic instrument coupled with reflector. This is a reflector basically, and it sends the electromagnetic wave or maybe any optical wave, and ultimately it reflected here. So that is the main working principle of the instrument. So EDM instrument, so this is the actual EDM instrument which we use on a site. So this instrument we call it total station. So even in our laboratory also we have one instrument, this total station instrument. So it is usually integrated unit called EDMI. What is the full form of EDMI? EDMI, right? Instrument. So EDMI is electronic distance measuring instrument, right? EDM is electronic distance measuring instrument. So consists of a electro wave generator, because we are sending the waves, right, from we are transmitting the waves from the instrument to the reflector, is not it? So that's why electronic wave generator is required. An oscillator, because in a wave there will be oscillation, so that's why oscillator is required. A modulator is required because you have to control the modulation. A transmitter, because you have to transmit it also, right? A transmitter is also required, and the receiver, because once the wave is reflected from the reflector, it will again come to in this instrument. So there will be a receiver also, that receiver will receive the signal. So the type, range and the accuracy of EDM depends on the type of wave carries it can generate and subsequently can transmit receiver. So this is a table you can see, basically two types of waves it can generate depending on the instrument. First one is the optical, right, there is total frequency in the light range, right? We have the visible light, we have the microwaves, we have x-rays, gamma rays, right? Depending on the frequency of light, we will have different types of waves. So if you, some instrument will have optical, means optical range, it will be sending the signals, and some will be microwave, right? We'll be sending a microwave signal from the EDM, and ultimately it gets reflected and it come back to here. So now you can see the accuracy of the instrument, right? See, microwave accuracy instrument, the base frequency, in that frequency there basically it runs. So modulated frequency is this one, and the range is 30 to 100 kilometer. Can you imagine? So total maybe 30 to 100 kilometer. If it's straight, it is visible, then you can take measurement using a single instrument, so you may not need any intermediate point while measuring that distance. So that's how so good basically in the micro, this instrument is EDM instrument. And you can see the accuracy, it is plus minus 15 mm plus 5 mm per kilometer. So you can imagine per kilometer basically you have 15 mm to 5 mm, right? Means almost 1 centimeter maximum error you will get it. So now what we have understood is, using EDM instrument basically accuracy will be very high, and in the long range we can measure the distances. So this is the reflector which I was talking about. So in the last slide you have seen the EDM, that is actual instrument, and this is the reflector. So reflector is consist of one or more corner cubes prism. So inside that, see, this reflector also will be mounted on a tripod, and this type of prism will be there at the center. So this prism will basically reflect the wave, a signal which is coming from the EDM instrument. So in which the sides are perpendicular to each other. So basically inside this prism the sides are perpendicular to each other in order to get the incident light reflected parallel to itself. Parallel to itself means the reflected light, whatever angle or whatever line it is coming, that the original line, emitted line, the reflected line also should be parallel to each other, right? Then only we'll get the exact distance. So for example, let me draw it here. So maybe something prism, something like that. So the which light is coming, this is the emitted light, so in this direction light is coming, so the reflected light also should be parallel to each other, right? So this should be parallel to each other, something like that shape has to be made. So this type of arrangement is there inside this reflector, and ultimately it reflects back the light into the receiver. So now the principle of working of the instrument. So the basic principle of EDM instrument is the determination of time required for electromagnetic waves to travel between two stations. So here the velocity of electromagnetic wave is the basis for comparison of distance, right? That's what, as we mentioned. So for example, here you have the instrument. So let me draw a tripod, and here you have the EDM instrument, right? In that something you are sending the laser light, and at this point you have the reflector. So maybe here you have the reflector, right? On a tripod, reflector also will be mounted somewhere, something like that. So this wave will be coming from this angle, and ultimately it gets reflected, and again it will go in this direction, is not it? And somewhere we have the receiver at this point, so it will be receiving the light, so receiving the signal. So how much time it took total? So we know the velocity of the wave, microwave or whatever it may be the wave. So we know the velocity of this wave, and we know the distance also, right? So now we know the time taken to travel, from this point to this point, that also we know. So from there easily you can find out the distance, is not it? So the distance will be simply uh, velocity, or basically time taken. Let me do it. So the distance will be simply velocity into t, right? Vt. So distance is d. So from this point to this point we are measuring, this is capital D. And velocity of wave already we know, right? If you are sending a microwave, then you know what is the velocity of microwave in atmosphere, and t is the total time taken. Time taken from here to here, and this is total distance, right? Two times the distance. So this will be divided by two. So entire. So because we are considering light signal will be going here and reflecting back here, so it is double, right? Two times. So that's why single d will be vt by 2. So that is our working principle of this EDM instrument. So now the principle of working of electro-optical instrument, let's see that. So electro-optical instrument are set up on a one station, emits continuous wave, carries a beam of light. It generated in a transmitter and modulated by the electronic shutter before entering into the aiming optics. The modulator chops the beam into wavelengths that is proportional to the modulator frequency, which wavelength is given by this one. So what will happen is the electro-optical instrument means there basically we are setting the beam of light from the instrument, and in the other side you have a reflector or the receiver also sometimes, so that will receive the signal, optical signal, right? So the wavelength of this optical wave will be v by f. What is v? V is the velocity of light through the atmosphere. So velocity of light already we know, right? What is the standard velocity of light? 3 into 10 to the power of 8 meter per second, is that it? So this is the velocity of light in a atmosphere, normal atmosphere. That is the value we consider. And f is the frequency, and gamma is the basically, this is not L, this is gamma. Gamma is basically wavelength. So let me correct it here. So this is gamma. So gamma is basically the wavelength, right? So wavelength means, let me draw it here. So wave normally goes in the oscillation motion, right? So this is the wave is going, traveling, something like that. So wavelength means from this point to, again it comes back to here, so original point. So from here to here, this is one wavelength. So from this point to this point, one wavelength. So from this point to this point, one wavelength. So like this is the one wavelength we call it, right? So that is the velocity of light divided by the frequency. Frequency means in 1 second, how much, how much undulation is happening, how much full cycle of wave is completing, that we call it frequency, right? So velocity by frequency, if you get, you will get the wavelength. So the modulated light is transmitted to the reflector placed on the other end of the line. The reflector acting as a mirror, so reflects the light beam back to the receiver when the incoming light is converted into electronic signal. A phase comparison is made between the projector and the reflected pulse, then the amount by which the transmitter and receiver signals are out of phase get transmitted electrically and get registered by the meter by getting the converted into equivalent distance. So what it is mentioned is basically you have two instruments, right? One is EDM standing here, and apart from that you have the reflector somewhere here. So when EDM light goes and it reflects back, right? So here basically it is sending this type of signals. So this type of signal will go to reflector and it gets reflected. So once it is reflected, the phase of this signal also will change. So something like that phase change may be occurring. So phase change also will be there. So in the receiver end, receiver will be always connected on the EDM instrument, right? In the EDM, you have the receiver. So this receiver will receive this reflected wave and it will measure how much phase shift happened. Phase shift means, so this is original one, so and reflected may be out of phase, something like that, right? So basically it measures, so in the reflect or in the receiver, basically you have the phase meter which measures the phase difference between these two waves. One is emitted wave, another is the reflected wave, right? And that phase difference also will be recorded, and how many complete wavelength cycle it has completed from this point to this point, that also will be measured. So based on this, basically we find it out the distance. So in the even in the electro-optical instrument, right? If you are sending the optical light from, from the receiver, from the emitter to the receiver end, then the clear line of sight is also required, right? If any middle object is there, maybe a tree is there in the middle, then the light won't pass through the tree. In that case, you need the clear sight required, right, for that. But if you are sending some other rays, for example, right, microwave or some other rays, which if a small obstacle is there in the middle, maybe a thin obstacle, so microwave can penetrate maybe through this obstacle, microwave wave, and it will penetrate through this obstacle and it can receive there, right? So but optical light cannot pass through the obstacle. So if you are using the electro optical EDM instrument where the optical light is sending from, the instrument, then again you need clear line of sight, means there should not be any difference or many obstacle in the center. So that is the meaning here. Thus required intervisibility between the stations. Intervisibility should be there, similar to thing what we discussed in the taping also, right? In that taping or chaining, using the tape or chain, how we do the measurement, so in that also intervisibility of station is required, right? So that's why using this electronic optimal or electronic devices for the measurement, the measurement will be very much accurate, because here the signal is going on air, right? But using tape, if you are using, then what will happen? So ground will be undulated, is not it? So if you lay down the tape at the ground, then the shape or the alignment of the tape may not be straight. It may be also undulated, because of which you will get the incorrect distances. Even if you hold the tape on a air, something like one person is holding here tape, another person holding here tape, so the to the hair the shape of this tape also may be, in a sag condition, it may not be straight, right? Because two forces, two surveyor will be pulling this tape into two different forces, so ultimately the shape may be something like that, not exactly straight, not exactly horizontal. So in that case, again, you will have a more problem, but this problem is uh, easily removed using, if you use the electro-optical instrument or electromagnetic instrument for measuring the distance. So now the working of electromagnetic EDM instruments. So in the last slide, we have seen working of electro-optical instrument, right? As I mentioned, there are two types of signal you can send. First one is the optical signal, right? Optical signal means light, basically visible light we are sending it, and the next one is electromagnetic, it's microwave, basically we are sending it. So this one is working principle of microwave instrument. EDM instrument transmits high frequency microwave. So in that case, it will be transmitting the high frequency microwave, and this is most commonly we use. The measurement involves two interchangeable instruments, right? So one being set up on each end of the line to be measured, right? So the sending instrument, so in that case there may be two instruments. One will be, the reflector may not be there. In that case, you have one instrument here and another instrument is here, right? Both are similar instruments. So when you send the microwave from one side to one point to another point, so this receives the microwave, right? So this measurement basically involves two interchangeable instruments, one being set up on each end of the line to be measured. The sending instrument transmits a series of microwaves. So this instrument, maybe first will send the series of microwave which run through the line, which run through the entire atmosphere and of the receiving unit. Basically here it will be received and again transmitted to the original sending unit. which measures the phase difference, right? So again this instrument will receive it, and again it will transmit this with this one. Maybe you can use reflector also here. So in that case the microwave will be get reflected, and it will again come back to here. So again we have in the receiver one phase difference meter. So in the using this phase difference meter, you can measure how much will be the phase difference between the waves. So the net phase difference get converted into the linear distance. So in this case the intervisibility between the stations may not be required, because as I mentioned, microwave may penetrate maybe in a small obstacle, right? If a small tree is there, microwave can penetrate into it, so that you have, so that you may not need the exact line of sight, clear line of sight, right? If there may be a small obstacle is there, then microwave can pass through. But again, if a building type of structure is there, in that case microwave also cannot pass, right? So but a small obstacle it is there, then also it can measure the distances. That is the working principle of electromagnetic instrument. And in the last slide we have discussed electro-optical instrument, right? So now you can see the principle of measurement of distance using the EDM. So what is the principle? So as I mentioned here also, so you have a 2 point, right? A point here and B point here. So you have EDM at this point and you have the reflector at B. Right, that's all. In order to measure the distance between point A and B, let EDM be placed at A. EDM is placed here and the reflector is at B. Now the modulated beam transmitted from A travels to B and return back. So from here EDM basically you are sending a light, or maybe optical wave, or maybe a microwave also you are sending, and it will get reflected here and again it will come back here, isn't it? So here you have the receiver also in the EDM, right? As I mentioned, the EDM will have different component. One will be transmitter, another will be receiver also. So receiver will receive the signal and let the receiver signal is out of phase, right? Out of phase means what? So let's discuss that. So let me draw it here. So you have a signal normally passes through something like that, right? In oscillation format. So like that signal is going. So this is starting from here at this point. So this is, it completes one complete cycle. So again from here to here it completes another cycle. From this point to this point it completes another cycle. So total 3 cycles are there. So when it get reflected, for example here you have the reflector. So when it get reflected, now from here basically signal will be coming, something like that signal will be coming. So you can see these are sometimes out of phase. Out of phase means here it is shown clearly. Let me take color. So here to here you have one wavelength. So here to here you have second wavelength, third wavelength, fourth wavelength. Now when it get reflected, now see there the shift, little shift. So now wavelength will be from here to here. It is not exactly matching, the emitted person. This is the reflected one. Bottom one is the reflected wavelength, right? And top one is the from here to here how it goes. So top one is like that, but bottom one is not exactly in phase. So it is little bit of out of phase will be there, right? Because the reflection happened. So that we have the phase meter in the receiver end. So in that phase meter, it measures the uh, out of phase, how much phase difference is there. So phase difference is this much for this example, right? So ideally this should be at this point, but because of you have the phase difference here, so ultimately you have small phase difference, d, small d, and capital D is the total distance, right? So this phase difference we call it phi, delta phi. Delta phi is the phase difference. So total phase difference will be 360 degree, means out completely out of phase. So phase difference is delta phi by 360 is total maximum phase difference into wavelength lambda. That will be d value. D means this distance, small distance, error, not error basically. This is the phase difference distance. So that you can compute what is the small d. So small d and total how many wavelength it has completed. That also you can count it. 1, 2, 3, 4, 5. Right, in this problem maybe 5, 6, total maybe 6 phase differences, 1, 2, 3, 4, 5, 6, yeah, total 6 complete cycle it has completed, is not it? So 6 into wavelength plus d, you will get it, the total distance, is not it? So that is the thing. So to the d will be half of, why half of? Because to 2 times the wave traveled from here to here, and from here to again it comes to b. That's why whatever total distance we got it, we are dividing it by 2 into n into lambda. Why n into lambda? Lambda is the how many times, what is the number of wavelength. So for example, while going the signal, how many wavelength it completed? 1 2 3 4 5 6. So 6 into lambda will be up to this point plus small d. Small d means the phase difference. So n into lambda plus this portion, this small d, by 2 if you get the total distance from A to B. So that's how basically we are doing the calculation in the EDM. So when n is basically the integral number of the wavelength, means how many complete wavelengths are there, that is n, and as the total length is double, so basically that's why we are keeping it by 2. Okay, so now you understand the principle of EDM. So now we sometimes use decade modulation technique basically in the EDM measurement. So in decade modulation, a number of frequencies of multiple 10 are generally used. Now you see this type of, that phase difference is there. So what we do sometimes, not even single times, we take multiple times measurement. So all these things already given in the EDM instrument. So EDM instrument automatically all these things it will do it. So multiple measurements it will take, not only single measurement. Okay, so initially it will send maybe 10 megahertz wave. So let me draw it again. So you have EDM and you have here maybe a reflector. So at the first step, first measurement, it will send 1 megahertz. So, no, 1 megahertz wavelength of microwave, for example. So you will get one value, one distance value. Now next time, same measurement it will take with maybe, you know, 10 megahertz. It will send the 10 megahertz distance, and again it will measure what is the distance. Then 100 megahertz, like that 5 6 multiple different types of signals with different frequencies basically it will send and it will observe. So like that multiple of 10 basically we use, like 1 10 100 megahertz 1000 megahertz, like that multiple signals we send it, and every time we measure what is the distance between A to B. So the phase difference of each frequencies and thus equivalent distances is determined separately, and finally total distance has been computed, right? So this is the formula. Basically already we have seen lambda is equal to b by f. So if first initially if you are sending 15 megahertz, 15 megahertz is the frequency, right? You are sending a 15 megahertz wavelength, wavelength signal. So in that case what will be the wavelength? Lambda. So lambda will be v by f. V is what? Light of velocity of light. So that we know 3 to 10 to the power 8 meter, right? That is constant. 3 to 10 to the power 8 is the velocity of light, divided by, if you are sending 15 megahertz, 15 into megahertz you are converting into hertz, means 10 to the power 6 you have to multiply. So this comes out to 20 meter. So if you are sending 15 megahertz of wavelength signal, microwave signal or any signal, so in that case the wavelength will be 20 meter. Wavelength means, you understand it, wavelength is, so this is the wave is passing. So wavelength means from starting point to one single wavelength. So this is one complete cycle it completed. So this is, we call it lambda, one wavelength. Okay, so this lambda for 15 megahertz will be 20 meter. Okay, so that's why if you want to measure maybe a small distance, for example 10 meter is or 15-meter distance is there, you want to measure distance 15-meter distance, right? So in that case if you send 15 megahertz, 15 megahertz frequencies wave, then what will happen? The one wavelength is even 20 meter, but you want to measure 15-meter distance on the side, maybe small location, to A and B, two are very close to each other, maybe 10 to 15 meter maximum the distance. If you are sending 15 megahertz wave, then what will happen? The wavelength is 20 meter itself. One wavelength is 20 meters. So 15 megahertz may not be sufficient. You have to send, higher megahertz, higher frequencies, so that the wavelength will be reduced. Right. So one example here it is given. So now if you see, thus a full sweep of phase meter represents 10 meter distance, right? So that means 20 meter is the total wavelength, and half wavelength we call it, that is 10 meter, is not it? So half means up to this. So from here to here it will be 10 meter, from here to here it will be 10 meter, right? Total 20 meter is the wavelength. So half wavelength is 10 meter, right? That is, phase meter provides reading in unit of meter and its decimal part, thus the range of measurement distance is 0 to 10 meter. So if you are sending first 50, for example here to here you want to measure, so first time you have sent 15 megahertz wavelength signal from here. So what it will measure? It will measure the phase difference, right? Small d it will measure. So small d will be 0 to 9 meter in that range. So the if original distance from A to B is 4567.123 meter, then initially we are sending 15 megahertz. With that, the measurement will be coming like 7.123. Why 7.123? Because here you are sending 15 megahertz of wavelength. So 15 megahertz will have the total wavelength is 20-meter length, and half wavelength length will be 10 meter. So you can get D value 0 to 10 meter or 0 to 9.99 in this range. So you get first reading, you get it 7.123. So now in the first reading you got 7.123. Now you change the frequency of this signal. Now the signal will be 1.5 megahertz. Initially we have sent 15 megahertz and we got 7.13 meter. Now 1.5 megahertz you are sending. So the half wavelength, if you compute with this formula, you will get 100 meter. So 100 meter means basically now you can measure up to 100 meter. So you will get now 60 meter. Once you send 1.5 megahertz, you will get the answer is 60 meter. Phase difference is 60 meter. So next, again in third step, you send 0.15 million hertz megahertz, basically 1.5 megahertz again you are sending. So see, 10 times we are reducing. Initially 15, then 1.5, then 0.15 megahertz we are sending, then we will get it 500 something, right? So the value will be coming something like 500. So finally you send 15 kilohertz. So again you make it half, you get 15 kilohertz, you are sending the wave, and the distance you will get it something 4000. So now you have to add all the 4000 plus 500 plus 60 plus 7.123. So if you add all, you will get the total distance from A to B. So now you can see we are sending the various frequency levels of wave, not a single wave. Multiple frequency wave we are sending, and multiple measurements we are taking, and ultimately we are measuring the distance from A to B. So now in this EDM measurement also you will have an error, right? So what are the errors? The systematic error prevalent in the EDM measurement due to the reflection of the atmosphere, right? Because here the waves are passing in atmosphere. So, atmosphere, if it is, if humidity is more, then the maybe speed of some wave may be high or low. So this is depending on the atmosphere. So you will have an error in the atmospheric condition. Then you have the slope error. Slope error means, right, for example, your instrument is maybe a little tilted in that case. So you have reflector here, so reflector also will be little bit tilted. So in that case you will have actually, instead of measuring the horizontal distance, basically you are measuring the slope distance, right? So this is also a error, slope correction, you have to do it. Then the ground reflection, as you have to send the signal from the instrument, so the signal may be reflected to the ground. If any water body is there in the middle, so in the water body also the signal get reflected and it get interfered in the main calculation. So ground reflection also is a major problem in the EDM. And then you have the reflector offset. Reflector offset means if the reflector is not in the same line, then you may get the inclined line also. So that is the reflector, and then lastly we have the instrument error. So instrument error means basically, but the instrument also may sometimes, the sensors and all may not be working perfectly. So in that case also you may get some error, that we call it instrument error. So basically these 5 types of errors will be there in the EDM instrument. So EDM instrument is also not 100% accurate. You can see, you already have seen in the initial slides also, the accuracy is something like 15 millimeter in per kilometer, something like that, in that range. So these are the source of errors, how the error introduces into the measurement. So what we do is, so we take multiple measurements and ultimately uh, we take the average, and also we'll try to try to make the corrections because of error. We have some standard formulas for that: atmospheric error correction, slope correction, ground deflection, all these things. If you have any water body at the middle, then you may have this ground deflection phenomenon and all. So in that case, accordingly you have to correct the results measurements. So now the last slide in this topic is the non-linearity of EDM system. So as you have seen, as the light goes on increasing, right, as the length of the line goes on increasing, the error of the measurement distance using the EDM is repeatedly changing to a maximum, to a value non-linearly. Means if you take multiple measurements using EDM, then also every time you may not get the same value. There will be a small change, error in the value. So that is the non-linearity of the error in the measurement is determined by making use of series of stations placed at the precise intervals. So that's why instead of, so the error will be increased, right? If you want a to B, two station, you want to find it out. So if A to B's distance is very high, maybe for example 5 kilometers, then the possibility of error will be more in this instrument. So you may take intermediate point for every 1 kilometer, one instrument. If you measure one as one point, intermediate point, if you take and measure the distances, so that will give you more accurate results. So in the most of the EDM, factory calibration is performed. So the EDM also has to be calibrated, right? It is giving perfect result or not. That also we have to check it. So before doing into the actual field survey, first we need to calibrate the instrument. So factory calibration is performed, right? So in a factory, we will send the instrument, and the factory people will check whether the instrument is giving correct result or not, so that the average non-linearity also we can be reduced. So the calibration for non-linearity is needed when it is being used for the high precision project. So if you are using for the high precision projects, like construction of buildings, bridges, where the precision will be very high, in that case, the calibration of EDM is also necessary. So in this lecture, what we have seen using this electronic instruments also we can measure the horizontal distance, and this type of instrument is very much useful nowadays. So in modern surveying, we normally use this total station or this type of EDM instruments for measuring the distances. Either it may be horizontal distance or vertical distance or angles, anything. We use this instrument called total station, right, or EDM type, any instrument. So we have seen in this lecture what is the principle of EDM, and also how to measure the distances using EDM, and also lastly we have seen the errors, how errors are introduced in this EDM reading, and also how to make the corrections of them. So this concludes this horizontal distance measurement topic. So in the next lecture, or in the next lecture, we'll be starting a new unit, that is measurement of vertical distances. Thank you.